All right. So hi everyone. Thanks very much for joining today. Let me also take this opportunity to open up chat in the corner so that I can hopefully try and be looking for any questions as we go along. Yeah, thanks Nikolai for the nice introduction. Today, as was mentioned, we're going to be going through a pyhf tutorial, but at the same time, I want to make sure that there's some time left at the end to discuss upcoming work that's being done and some upcoming features that should be out quite soon. And so we're not going to have enough time to do kind of the full kind of normal hour tutorial because I want to make sure that we have time at the end to discuss the new stuff. So we're going to do a bit more of a high level overview of things. But we, at the same time, will make sure that people have the resources they need to get back to review things later on if they want. So starting from my presentation view or my contribution view on Indigo, the first thing I'm going to try and make sure that everything is run along with you, is I'm going to, I have two run-on bindery links. One of them is for the tutorial, and one of them is for the upcoming feature examples. So I'm first going to just go ahead and start both of these up so that I can go ahead and make sure that the container images get spun up and will be ready for us when we want. But for right now, we're actually just going to click on this first link, which is the pyhf user guide and tutorial. So if we click on this, so I'll also drop this in chat in case people, actually I'll be more useful. I'll drop the link to my Indigo contribution in chat in case people are trying to find that. Okay, so now we're at the pyhf tutorial webpage. I'll try and blow this up a little bit. So this is more just kind of a good overview page if you're new to pyhf in general and want to try and learn things. This is a Jupyter book that we have built and gets updated periodically, and then anytime there's a new release, we'll also go through and make sure that this is always up to date. So you can find this linked from both the GitHub repository as well as PyPI. But as you'll see here on the left-hand side, each of these little links is its own individual lesson that's mostly self-contained. So if you have questions later on about pyhf and you want to work through something, you can just come back here and click on any of those. And it also gives you some instructions on how to set up a virtual environment in different situations. And we won't be doing this today, but to kind of hint at a very interesting talk that Angus is going to be giving later today, it's also possible to run pyhf entirely in your browser. So you can work through most of the tutorial just in your browser without having to set anything up if you don't want to. Okay, so we can probably go ahead and get started, and we're going to get started by first doing a very high-level introductory to His factory models. So this is the view. This is the view that you get from the tutorial webpage, but this is the Hello World notebook. So what I'm going to do is I'm going to go back over to to Jupyter Lab and go to the tutorial session that I spun up, and I will again try and increase my screen size so that's hopefully easier for people to see. And the way that we're going to actually access these notebooks over here is we're first going to go to this book directory. And we can now see here that we have all of these different notebooks that just showed up on in the Jupyter Lab file browser. And so we see that there's one here called Hello World. So we're going to double click on that. And we now see that the same web page, the content that's rendered here is actually this Jupyter notebook that got rendered out by JupyterBook. So we're going to start stepping through here. Okay, so to begin with, so pyhf is the first Python implementation of the his factory specification for bin statistical models. So what does that mean? Well, in short, we can basically say that it's just a formalism that allows us to construct a bin statistical model in a nice simple format. And this is particularly useful when we're performing counting experiments that you might do, or that you would be doing in experimental high energy particle physics, usually at colliders. And so this the his factory formalism was created around 2011 as part of the work that went towards the Higgs discovery, and it's been used pretty extensively across different areas of particle physics ever since. It's used quite a bit in the Atlas collaboration, and it's used it or similar models to it are used widely across other LHC and collider physics experiments. So we aren't going to, for the sake of time today, we aren't going to actually step through all of the mathematical grammar of the his factory formalism, because that would take quite a bit of time. But if we jump back out to the web page view again, and we go down to this more information bit, you can see that there's this his factory notebook. And if we click on there, you can see that this kind of gives us a full overview of all the different statistical ingredients. But maybe the most important thing to do is just scroll down a little bit and get to this bit here, which shows us that we basically have the full statistical model ends up being a product of Poisson PDFs, as we're doing counting experiments, as well as constraint PDFs that allow us to bring into that'll allow us to use our information, our knowledge and information that we know about our detector and the physics that we're actually doing, to be able to constrain some of the model parameters. And then all of this gets tied together by the expected Poisson event rate, which itself is a function of both these unconstrained and constrained parameters. So this is just the important thing to remember here is that the main part of the model is a product of Poissons, and then you either have Poisson or Gaussian PDFs for these constraint terms. Okay, so stepping back to that though, if we now just kind of look at the model API, if we say we don't care too much right now of discussing the mathematical internals, but we just want to be able to build a very simple his factory model, we can do that pretty simply. So if we first just go ahead and I'll go ahead and blow this up one more time, even though that might be too big, but people can unmute or give me comments in chat if this is too big now. But if we go ahead and first do our imports, and then if we see that so we've imported pyhf as well as some things that we'll be using later on. We can see here that pyhf provides this, pyhf provides a whole model building API, which we'll get into in a little bit. But we also provide for some very kind of simple getting going examples, this simple models module, which has kind of a canned model for you called an uncorrelated background model. And so here we can see that this takes both a signal, a background, and a background uncertainty parameters, and we're expressing this as lists. So here there's just two entries in each. We'll see in a little bit that this corresponds to two bins, but if we go ahead and just execute this, we see that what came out is some sort of pyhf model object. And we can also interrogate that a little bit. So if we now dump this model specification, we can actually interrogate this a little bit. So, all right, so this is this is a dump of the model specification to JSON. So let me zoom out a little bit so that this fits on screen a bit better, but let's step through this just a little bit. So we have some jargon here. We have something called channels. We have things called samples, and we have things called modifiers. So to hopefully disentangle some of this jargon, in the His factory formalism, a channel you can basically think of as some sort of analysis selection region. So here we just have one channel that we're calling a single channel. But so you could imagine this as maybe our signal region, but as the His factory formalism allows for doing simultaneous fits, you could imagine a situation in where we have many channels, one channel for every selection that we have for our analysis. So we could have our like a signal channel, as well as maybe another channel where we might be inverting our cuts, our selection cuts, to try and have like a control panel, or a control region. So here today, for this very simple model, we just have one single channel. And then inside of it, we have these samples, and the samples basically represent the different physics processes that you care about. So here we just have two samples. We have a signal sample, and we have a background sample. And so this represents both the signal contribution as well as our background contributions in this region. And then we see that the data for both of these, there's these two, it's a list of two items, and this represents basically two bins. So we've constructed a model, a 2-bin model. So this is basically, we've binned our channel into 2 bins, and these are basically the yield counts for both the signal as well as the background process for in both of these. And then we also have these modifiers, and modifiers allow us to affect these are either additive or multiplicative factors that are going to affect the expected Poisson event rate. So these allow us to encode different systematic uncertainties and bring in information that we know about the detector or the physics process that's happening here. So here we can see that the signal sample, it is affected by a modifier that is called norm factor, and this basically ends up being an unconstrained normalization factor on a parameter called mu, which ends up basically being our signal strength. So this is basically just saying we want to be able to scale our signal strength up and down, and so we want to apply we want to be able to basically have a handle that will allow us to just do that, and this takes the form of this unconstrained normalization factor called norm factor. And then for our background model, we have this modifier that's called an uncorrelated background uncertainty, and this basically is controlled by 2 parameters that basically is saying that for the first bin, we're going to have a background uncertainty. Excuse me, an uncorrelated background uncertainty of 10%, and for the second bin, we're going to have a background uncertainty on the order of 20%. So this basically is just stepping through what the JSON here, because we dumped this the model specification into JSON, what this actually looks like. If you want to be able to go through and step through some of this in a bit more detail, this is also further explained in this His factory more information, as well as these different modifiers. We have a whole section because there's many of them, and they can maybe some of them are maybe not as intuitively named as you would expect. So we have a whole notebook that is just dedicated to those. Okay. So this is the specification, but let's actually explore what this model looks like a little bit. So if we evaluate this next cell, and I'll zoom back in again. Okay, we can now see that we're able to, through this model configuration API, this model config, that we're able to get a lot of information quickly about the model in some text format. So we can ask for the channels, and we see that there's that this is called, we have one channel, a single channel. And we can then ask about the number of bins in each channel, and we're told that there's 2. We can also ask what are the physics samples that are contributing, and we have background and signal. And we can also ask about the modifiers. So again, we have this, we have both the modifier type of norm factor and shapesys, as well as the names of the names of the parameters that correspond there. Which we can see here. And then we also have this stuff called auxiliary data. So what is auxiliary data? We'll kind of go over this quickly. We're not going to step through the whole bit of it, but the short information is that, as I mentioned before, we have these this main part of the the his factor model PDF, which is this product of Poissons across all bins and across all channels. But then there's also this second part, which is this auxiliary constraint PDF. And so we have auxiliary data is basically the information that we're pulling from from our information about the physics that we already know, to be able to give us parameters to evaluate these auxiliary PDF sets. And then these auxiliary PDFs have these nominal parameters that we call auxiliary data. But then they also have their constrained parameters that during the fit basically allow us to provide constraints on the rest of the model. Okay, so for the interest of time today, I'm not going to actually step through all of this, because this will probably take us quite some bit. But if we go ahead and evaluate, so this table here basically goes through and gives us, this is this high level view of these modifier and constraints that I referred to earlier, that summarize for us what are the different modifiers that you have access to inside of pyhf just by default. These are the ones that are defined in the original his factory specification paper. But this table also explains to us how are these how do these enter into the constraint terms, as well as are the actual model parameters. But the important thing here is, if we take this table and we take the information that we have about beforehand, where we said that we had, if we scroll back up, we said that we had a 10% and 20% background uncertainty on this uncorrelated background uncertainty shape systematic modifier. If we go ahead and by hand put these numbers in and calculate what our auxiliary data are, then we can do that by hand, but we can also just ask for it directly from the model configuration. Okay, so this means that we have a nice API that allows us to get at it, and that's good. So we can now look at data and the parameters. So we have a model, but we now want to actually be able to interrogate the model and ask it about what its predictions are. So if we just go ahead and run model expected data with no parameters at all, we can see that we get an error. And indeed, it says that we're actually missing a required positional argument of pars. So this kind of gives us a heads up. So that means that we we can't just ask it for what are the expected data with no information. We also need to give it the parameter values that we'd like it to be evaluated at. So that we actually have 3 parameters here that we need to evaluate. We have one parameter which represents the signal strength, and then we have 2 other parameters which represent the per bin parameters for this shape systematic modifier. So if we could just go ahead and set each of these model parameter values to 1 to begin with, then that means that we now have we're passing in as a list 1, 1, and 1. And now when we evaluate, we actually get model prediction. So what's coming out of here is we're saying if we set the model values or the model parameter values to 1, 1, and 1, and then ask it for a model prediction, then this is what comes out. However, this might look a little bit confusing at first because we said that we had a 2-bin model, but what's actually coming out is 4 numbers. So that might seem a bit strange, but we can reflect on the fact that in addition to this, the 2 physical bins, we also have the bins that correspond to these to the auxiliary PDF as well. So this is basically saying these are the expected these are the model expectations for the main part of the Poisson PDFs, and then these are the model expectations for the constraint terms. And indeed, if we actually evaluate this again, but if we say turn off the auxiliary data, then we just get back the expected yields for the main part. And so we were able to get here by asking for expected data by turning off the auxiliary data, but we can similarly just use this model expected actual data or model expected aux data to get both the main part as well as the auxiliary part. Okay, so that's fine, but we now might also want to be able to get information on how to actually interact with these model parameters, because so far we defined them once or they were actually defined for us already when we built this model, but we'd like to be able to interrogate the model's parameters a little bit more. So we can do this again by using this model config API by asking for the parameters, and if we evaluate that, we see that we get this we get these names of mu and uncorrelated background uncertainty, and similarly we can also ask for what the modifiers are, and again we see that we get information on that we have modifiers that are affecting mu and the uncorrelated background uncertainty we have a norm factor and a shape systematic. But okay, so this is fine, but when we were actually setting up the model beforehand, when we put in the different information, this might actually not always reflect if we ask for the parameters that come out, this might not always be the same parameters that we put in originally. The ordering might be different because it's just a list. So we want to, when it's constructed, it's a dict and things get moved around internally. In this situation, we can actually ask for the ordering of these parameters. So when we ask for the model parameters, what comes out, we can basically say in what order is this information being displayed to us, and this is what this parameter order is. So this means that the first model's parameters that come out is mu, and the second model parameters that come out is the uncorrelated background uncertainty. Okay, so again though, this might so if we want to actually ask about the model parameters, because we were using 3 numbers beforehand that were assigned to only 2 parameters, how does this actually happen? So again, we only have 2 bins in the model. So when we evaluate the model config and ask for the number of channel bins, we just get 2. But remember, one of these parameters that's configured by just one parameter, this gamma parameter, is a parameter that represents a factor for each bin in that sample, or each bin in that channel for all for both of the samples. So we can ask for information about this parameter set, and here we pass in the name of the parameter, which is this uncorrelated background uncertainty, and we see that what comes out is we get by default we don't actually get any information, but we can see that we get some informational we get some kind of lower level information, and that we can see that this sort of parameter, this uncorrelated background uncertainty, is constrained by Poissons. And if we actually ask for the number of parameters that are in this parameter set, we get 2. So even though we only had 2 bins, we have the number of parameters that are actually kind of present for this uncorrelated background uncertainty is 2, and then we had 1 more that came from the signal strength. Okay, so if we now look at the parameter defaults, so we can say that, all right, we need to try and think about how we're going to evaluate these parameters, and we can go ahead and, instead of having to have you make guesses right away, we can actually just ask the model to set some default configuration. So to begin with, we have this model configuration API, and we can ask it for suggested initializations for all of the model parameters, and here it's just going to return 111 by default. We can similarly ask for the suggested boundaries on all these model parameters, because they don't run from negative infinity to infinity. We can set some informed ideas on what these should be by default, although you can go ahead and set these as well. And then we can also ask if any of these model parameters should be held constant during the fit. So by default, all of them are false, which means that all these model parameters get to float around during the fit. But if we were to set any of these indexes to true, that means that model parameter gets pinned and everything else can float around it, but it's not going to change. So we can now actually use this information to get these initial parameters from the suggested initialization. And we can now ask, going back to what we did earlier, we can now ask for the expected predictions from this main model components by asking for the actual data, by passing in these initialization parameters, and we again get what we saw earlier of a prediction of 55 events in the first bin, and a prediction of 70 in the second. Okay, so we might also want to be able to figure out, in our model, there's a particular parameter of interest that we care about, and we might also want to be able to gain access to that easily. And so we can do this instead of having you to go through and traverse the whole model. We can instead just ask you to select the parameter of interest index, and here we see this is the 0th inside the construction, this ends up being the 0th entry. And now if we want to actually change something about that, we can do this by first saying we're going to copy these initialization parameters into a new variable called background parameters. And we're now going to say that so if I edit this on the fly, so if we look at what the background, if we look at what the background parameters are, at first we get 1, 1, 1. But now if we can go ahead and say that we want to set the background parameter that corresponds to the index for the parameter of interest to 0. And so now we're saying that we're set, so this now gets set to 0. And so with that information, we can also now evaluate what would be like this background only model with no signal components. And we see that we now get a different number because this is essentially just asking for the model evaluated under this background only model hypothesis. And so we see that instead of, we now just get 50 and 60 compared to this 55 and 70 beforehand. Okay, so far this has all just been about model building, but PyHF also provides some high-level statistical inference APIs. So at the end of the day, we're doing maximum likelihood estimate fits given profile likelihood ratio. And so if we want to set up what this, some of the typical patterns here, the first thing we need to do is be able to construct observations to give us the data to evaluate our model at when we're performing, when we're evaluating the log PDF. And so the very first thing we're going to do is create this observations object, which is basically going to say what we think the what it was the recorded data here. So let's say we did our experiment and we saw in that when we counted the actual data, we saw that we get 53 events in the first bin and 65 events in the second bin. If we then also put in this information about the auxiliary data, then we have observations for the all the observations for the full model. And so what we can now do is use this model.logPDF function, where we're going to say that the parameters of the model are going to be evaluated under these, what I said earlier were this the background pars, which is where we just have manually set the signal component to 0, or the signal parameter of interest, or the parameter of interest index to 0, and then we're also evaluating this log PDF function at these observations, and we actually get out some number. And so this is just our log PDF that's evaluated there. Similarly, if we can evaluate this again under our initial parameters, and we see that we get a slightly different number. Okay, so if we want to actually perform a fit, then we're going to need to use our PyHF infer, our inference API, to be able to do this. So now that we have our observations for data, as well as a model that we can pass in as a PDF, then we can now actually use this maximum likelihood estimate fit API to perform a very simple MLE fit from of the model to these observations. And what comes out here is the best fit model parameters for both the signal strength, which was this mu parameter, as well as the different parameters for the background uncertainty. Okay, so this is under the best fit. But now, if we want to say we don't only want to do maximum likelihood estimates, but we now actually want to do hypothesis testing. So we want to be able to say if we have sensitivity to a new model, or if we're able to reject a model hypothesis, then we can use the so PyHF implements this through profile likelihood ratio fits that take the form of using using asymptotic approximations through using by computing what we call this CLS value. I'm not going to go over the entirety of this, but this is a test statistic that was created around the time of the or was created in the Tevatron days and has kind of evolved and allows us to have basically characterize the analysis sensitivity to new signal while conditioning that on the background information so that you don't end up rejecting things unnecessarily. Okay, so if we go ahead and if we skip all of this formalism so that we actually have time to get on to some of the new things, we can see here that we have this hypothesis testing API. So this asks you for a model for a parameter of interest value. So basically, what value are you going to test your hypothesis at? It then also asks you for your observations that you want to evaluate things at, the model you want, as well as the test statistic you care about, because there's multiple test statistics you can evaluate at, depending on what's the sort of hypothesis test you want to do. And then this return expected set is also just saying don't only return to us the actual observed fit, but also return to us the parameters under the plus and minus 1 and 2 variations. And so if we go ahead and evaluate this, then this was correct, but we also noticed that we got some warnings here. So what's going on? This is because we asked for one particular test statistic Q, but this test statistic ends up being interesting to us in under different model hypotheses than the one we actually care about. So we're going to go ahead and to edit this a little bit. So we can see here that we care about this in situations in which this Q test statistic happens when the signal, the parameter of interest can dip negative, but we're actually constraining this to be positive by setting a lower bound of 0. So we're going to switch the test statistic to be one that we care about when we're trying to exclude or trying to exclude set limits in the presence of a signal contribution that we think would only be additive, and so there couldn't be interference. And so now if we go ahead and evaluate that, we see that we get the observed test statistic that we care about, as well as the test statistic under the expected the background only, which is the expected, and then we have the plus and minus 1 and 2 sigma variations. Okay, and then we can also so that's fine, but we might also now want to do some upper limit testing. So if in the situation in which we have performed an analysis like a search, and we looked for the presence of new signal, but we weren't able to find any, that we can now go and actually do a scan to try and set best limits on the model parameters. pyhf provides kind of a nice high-level API for you, where you can again set this up with the observations, the model, and then now instead of giving it a single parameter of interest tested to a single parameter of interest to test, you can instead give it an array. And so this is now going to be the different values in which it will step through and actually evaluate the parameter of interest to test. You can also set the alpha for it, where this, if we care about the 95% confidence level, then this alpha that we're going to be assigning for the level would then just be one minus that, so 0.05. And we can see here when we perform this very coarse, because we're doing this for just this demonstration upper limit exercise for both the observed and expected, then we get so these return values here are then the 95% confidence level upper limit on the signal strength. So this is what we actually care about when doing the limit setting, but we also might want to be able to visualize this, especially as at different stages in the analysis when we're trying to play around with different test models to try and make sure that we understand both the analysis, the modeling, and all those other components. So we also provide this this contrib module, which provides some visualization features, even though this will eventually get spun out into its own visualization library. So here we can then basically take this information again. So we're going to if we look here, we said return the results, and so we have this results object, and so this information provides us all the information we need to visualize things, again with the parameter of interest values that we looked at. And so this is what's called sometimes as a Brazil band plot, which basically shows us visually what the expected or what the observed CLS value was, as well as the expected CLS values at the nominal ±1 and ±2 variations for all the different model or for all the different test parameter of interest values that were tried. And we can see here we've also drawn the power, evaluated in alpha 0.05 as this red band here, and we can visually look and see where the black solid band crosses this red band, and this is where we can say that we've excluded this model. And if we go back up here, we can see that again this was at the actual computed value is 2.5, and we can see that's where this is crossing here. So here we had to do a little bit of all this, by hand in some sense, but we can also have this. Sorry, that was with our kind of, upper limit API. But if we also wanted to do this by hand to just be able to step through and control things a little bit more, you could also do this simply by just doing this in a loop, and you can see that we get the same results. Okay, so this has been kind of a very high-level overview of just model building as well as the start of evaluation. But I now want to try and take the last 10 or 15 minutes or so to switch gears a little bit and talk about things that are going to be coming up in the next release of pyhf, as well as some interesting things that are happening in the broader ecosystem. So to do that, I'm going to go back to this pyhf, to my contribution on the Indigo agenda. And now there's this run on binder upcoming feature examples link. So if you go ahead and click that will now launch you over here into a new session. Okay. And then it looks like it looks like this was dormant for long enough that it went ahead and actually the server got shut down because it didn't detect any activity. So this hopefully won't be happening for you. Okay, that's interesting. It's not showing any of my files. So I'm going to go ahead and say that that's a bug, and we're now going to just launch that again. So upcoming feature examples run on binder. Okay, so here, because this was generated, this notebook was generated, we're just going to say yes to selecting this kernel. Okay, so this is going to be, I want to make sure I have time for questions. So this is hopefully going to be less than 10 minutes, just kind of talking about some upcoming features and development. All right, so here I'm just going to evaluate these for later on. But so coming very soon will be pyhf version 0.8.0 release candidate 1. So at the moment we're on pyhf version 0.7.4. And version 0.8.0 has been worked on for quite some time, and we were hoping to actually have this release candidate out as of last night, but life got in the way a little bit, so we didn't quite hit this, but we can still talk about features that will be available soon. So a very highly requested feature, which is a nice way of saying one that's been asked for a long time, but we've been a bit slow to get to, has been the ability of to have custom modifiers. So beforehand in the user guide, there's this modifiers section, which kind of goes over all of these different modifiers and explains to you how you can maybe use them. But at the same time, there's just a set of them, which ends up being a sufficient set of building blocks, but there's plenty of analyses if you're doing something like an effective field theory analysis, or maybe you're doing something a bit more complex that doesn't nicely fit into the original His factory formalism, where you need a bit more flexibility than just that set of building block modifiers. And you have some idea of a functional form that you want this modifier to take, but you don't have a way to express it in pyhf natively. So we've to deal with this in the upcoming 0.8.0 release, we've added this experimental extra, which once it's out, you'll be able to access with just doing pip install pyhf and then asking for the experimental extra. And that will include some additional dependencies that we're still trying to feel out if they will be a good fit. But here we can see that this also will have this experimental module. And if we import these modifiers, we now have access to experimental modifiers. And this now allows us to create some new parameters, parameter M1 and parameter M2 that have some initialization values, as well as model parameter bounds. And then we can now say that we want to create a new custom modifier that is going to be a custom type, is going to be able to operate on these two types of is going to be dependent on these two types of model parameters, and then actually give it these model parameters. Once we do that, we can now actually construct a model that uses this information. So here, if we look at these modifiers, instead of being something like the norm factor, or this uncorrelated shape systematic, instead we now have a modifier that's of this type custom. And if we look at what's actually the data, or how this modifier is defined, we can see that we're able to give it a expression of just and here it's just a constant M1, but for our signal. But here for the background, we can see that we can give it a string expression that ends up being M1 plus the square of M2. So now using this some of these optional, or these extra dependencies that are in this experimental extra, we're able to start allowing to have array-based string expressions that allow you to be able to construct these custom modifiers. And so you also need to specify the fact that you're using a non-standard modifier set, but at the same time, when you go ahead and construct that model, if we now ask for that model, it still exists. And if we ask for the modifiers, we see that they're here, both of type custom and with names F1 and F2. And if we actually evaluate this now, then we get reasonable predictions out, which is great. So this will be upcoming and be able to be tested soon once the release candidate hits PyPI. So please be on the lookout for that. I'm starting to run a little bit short on time, so I'll try and speed up a bit. But I'm not going to try and steal any thunder here and discuss the API for some of this really nice work. But you should all check out Malin's talk later today on Bayesian and frequentist methodologies using pyhf. And I'm just going to point out that things like this now exist, so we can see that there's now these libraries like Bayesian pyhf that actually have infer APIs and also allow you to take a now Bayesian approach to statistical model building as well as statistical inference using pyhf to still do the model building for you. So that's something to maybe check out if you're interested in. So here there's this whole Bayesian pyhf small library that was written to extend this, but something we'd like to do in the future is now develop a plugin system for pyhf to make it easier to build tools on top of things. So currently, to be able to use Bayesian pyhf, you have to first import pyhf and then import Bayesian pyhf, or this would be if you want to use both the pyhf API and the Bayesian pyhf API, you'd have to import both. But what we'd like to do is construct, and what we plan to do in the future is construct a plugin system. So all you would have to do is install both pyhf and Bayesian pyhf in an environment, and then just by the fact that Bayesian pyhf is installed, then you'd be able to just simply import pyhf and then have access to some sort of, and then you would automatically have access to an API like pyhf Bayes. This isn't a real API, but this is just kind of giving you the idea that before there is right now no pyhf Bayes API in pyhf, but this would be automatically discoverable and usable. And in addition to being able to create a plugin system that would allow for extension of pyhf's inference and model building API to do cool things like that, what we're also interested in doing is leveraging some of the recent advances in the Python array API standard, such as this first implementation of the array API compatibility library, array API compat, which now basically provides a single compatibility layer for any library that implements the Python array API standard, which is currently implemented by NumPy, CuPy, and PyTorch. For those of you who don't know, CuPy is basically the NumPy API, but implemented with CUDA kernels so that you can do NumPy-like operations on the GPU. JAX is also in the process of implementing this, and there will hopefully be more that follow. But the cool thing here is that if you go ahead and use this array API compat library, you can write a function that takes in array arguments, and you can then use the array API compat to move them into a namespace that where the operations are agnostic. But that means that, so for this function here that was written once using the array API compat library, we can now construct NumPy arrays and pass them to this example function and have this get evaluated. But we can also construct PyTorch tensors and pass them to this function, and they also get evaluated just fine. Okay, so that's the exact same code that was written here, but evaluated using two totally different libraries that by default aren't interoperable with each other, but now are. And we don't have GPUs available today, but if we had CuPy installed, we could do the same thing with these by constructing CuPy arrays and passing them in. And this function would also get evaluated on the GPU and return to us the same thing. So you might say, well, doesn't the pyhf TensorLib shim layer kind of already do this for you, and that you're able to so you're able to use both NumPy and JAX and PyTorch and TensorFlow as these different computational backends. And while we do support these are also backends that we've had to hand implement. And so if we instead revise pyhf to use the array API compat library, then that means that while we can still support internally with pyhf things like JAX and other libraries that might not have full implementation to the API standard yet, if you have any array library that implements the array API standard, then you could implement a tensor backend yourself. And basically now you can imagine a plugin system of different tensor library systems that could be arbitrary and highly performant. This means that we can also focus more on the optimization of pyhf rather than having to worry about the different having to worry about maintaining all these different backends simultaneously. For more about pyhf and in the broader ecosystem and also backends, I'd encourage you to check out Jack's talk on Thursday all about SPAY and how he's been able to implement this plugin system that allows you to optionally use pyhf with his SPAY library. Okay, as I'm running out of time, just to close up the things that we have coming in the near future is, as Jonas mentioned previously in the week, there's this high energy physics statistics serialization standard, the HS3, which is currently being worked on. There's a implementation of HS3 that currently works on root master, but there's planned implementations that are moving forward with pyhf as well. And this is, we think, quite important, as this will allow us to move forward towards having a write once for models and then run anywhere in the broader high energy physics ecosystem. And so if any of this today has seemed interesting, or if you'd like to learn more about how to use pyhf, or if some of these new features that we're going to be rolling out soon sound interesting to you and you'd like to get involved with development, we're also having the first pyhf workshop at CERN from the 4th to the 8th of December this year. There will also be a remote connection, but if you're interested, we'd highly suggest that you check out the Indigo, which has more information about the workshop, as well as how you might be able to come if you don't think that travel might be reasonable for you right now. Yeah, so hope to see you there. And with that, I'll go ahead and end. And I think I unfortunately went a bit long, so we may only have a few minutes for questions, but I'm more than happy to try and answer any.
Okay, yeah, thanks a lot for this really nice and extensive tutorial. Yeah, I'm really glad to see that start implementing this array API. That sounds very interesting. So are there any questions?
So I can't see the list, but I see that Luigi has a hand raised.
Yes, hi Matthew. Thanks for the very nice tutorial. I really learned a lot. So my first question is maybe was more curious about the test statistics and toys. So you showed your examples, you showed you've been using these test statistics, and I guess pyhf was using their asymptotic form in the back. So I can imagine that, yeah, okay, there's also a full functionality for generating these toys. So I was wondering how, I was wondering first about, let's say, whether performance of all of this, whether this is fully functional and usable. In general, can you say a couple of words about, let's say, the functionality that is available there?
Yeah, so I guess I would say that, excuse me, no, apologies. Yeah, so for the pseudo experiments API that we have implemented right now, it does work. There is a bit more that we could do to try and make things a bit nicer. So in general, if your model, if you have a model that is, I guess I would say, well modeled, and you've given it, you've taken some time to think about the model building, then we have seen that everything works quite well. And granted, it's been quite some time, so more than a year since we've actually put things, done pseudo experiments on GPUs and actually done some testing of how that works. I'm not going to claim that the pseudo experiment generation is totally optimized, because it isn't at the moment, but it does work, and we have had some Atlas analyses use it. However, the kind of going through and overhauling the internals to make pseudo experiment generation a bit nicer, and also make sure that we make it so some of the edge cases that don't hit people quite as hard or unexpected is on the to-do list as well. But in general, I would say if you have something that is, if you have an issue with anything in the pyhf API that you feel is not good, or if you think is confusing, squeaky wheel kind of gets the grease. So please come and open up a GitHub discussion and talk to us about that. And if you think that there's that this is something that isn't just confusing in the documentation, but it actually needs to be improved, please open up an issue, and we're more than happy to iterate there.
Yeah, thanks. I mean, actually, I've been working on these things, building own tools in the past. So I never used PyHF, so I would be very curious in the future to try it out for doing the same. Maybe I have a question. Maybe it's maybe more specific, but you can say something. Maybe
Sure.
example, we've been extensively using what at least in the PDG is referred as the Bayesian hybrid, Bayesian frequentist hybrid way of generating pseudo experiments. So I was wondering, for example, whether it's possible to sample the value of nuisance parameters from certain priors, or that, for example, is covered in the Bayesian package PyHF that you mentioned, and there will be a talk about later. Is there this functionality available for let's say
so I think the short answer is probably not the way that you want it. So this would be something that we could definitely discuss, but I think for the way that the pseudo experiment generation is implemented here is kind of following the PDG recommendation. So this is, as you said, this like hybrid implementation. But if you want to be able to start now, if you actually want to be able to start doing full Bayesian prior manipulation, then this is the API that we have right now is probably not the one that you want.
Okay. So at the moment, for example, if I define a modifier for a nuisance parameter, and that is varied in a certain uncertainty when creating the toys, is that something I expect PyHF to do, for example? And I'm not sure I'm maybe asking the right question, I hope.
So if you at the moment, if you just use the modifier building set that we have, if you go ahead and basically build your model and put in all your model, if you build the model with all the modifiers, sorry, I keep on wanting to say parameters. If you build a model and include the modifiers, then during the pseudo experiment sampling, those do get varied appropriately.
Okay, thanks.
Yeah, there's I might maybe what I can do after this is send you a link to a GitHub issue where thanks to a contribution for Mason Profit, there was a bug in how we were doing this, and this got patched about a year ago. And if there's additional questions, on the actual implementation, that would probably be a great place to continue that discussion.
Okay, thanks. Great.
Okay.
I guess I have other questions, curiosities that we can follow up offline. It's running out.
Right. Yeah.
Thanks much.